In this video, we're going to talk about definite integral. In the last video, we talked about approximating the area underneath the curve using RAM, rectangular approximation method. And we found out that the more rectangles you have, your approximation gets closer to the actual answer. Now, when you see the word Riemann sums, I want you to think about the process. It's the process that you're creating infinite numbers of rectangles so that your approximation is actually the actual answer that you want. So this is what I mean. Remember, n represented the number of rectangles or subintervals. We're letting limit as n approaches infinity. What does it mean? That means you're creating infinite number of rectangles underneath the curve. And f of c of k represents the height of the rectangle. And delta x is the width of the rectangle. And this summation notation means you're adding up all the areas of the rectangles. And when you say limit as n approaches infinity, that means we're saying that we have infinite number of rectangles underneath the curve. And this is a process of finding the actual area underneath the curve. And another way to represent this is using the integral sign. And this is what I mean. This is a sign of integral, and we call it the integral sign from a to b. A is called the lower limit of integration, and you know where a, b, and comes from. And b is the upper limit of integration. F of x is called the integrand, and that represents the height of the rectangle. And d of x is the variable of integration, which represents the width of a rectangle. And we call this whole thing integral from f from a to b. And when you find the value of the integral, you have evaluated the integral. So when they ask you to evaluate the integral, you got to find the answer to the integral of f from a to b. And we'll look at more examples later on. Now we could find the area under a curve using definite integral. So if y equals f of x is non-negative, which means it has to be 0 or positive, and integrable over a closed interval a to b, then the area under the curve, y equals f of x from a to b, is the integral of f from a to b. And let's take a look at some examples. By the way, before we look at examples, we need to talk about existence of definite integrals. All continuous functions are integrable. That is, if a function f is continuous on an interval from a to b, then its definite integral over a to b exists. So in order for definite integral to exist, f has to be continuous on the interval. So he says evaluate the integral of x from 0 to 4. So how can you evaluate this? Our f of x is x. So let's graph x from 0 to 4. So when you graph y equals x, this is what you get. And when you want to integrate x from 0 to 4, basically we're finding the area of this triangle. And what is the area of this triangle? It's going to be 1 over 2, the base, which is 4, times the height, which is also 4, and you get 8. So when we evaluate this integral, we get 8. So let's evaluate the integral of square root of 4 minus x squared from negative 2 to 2. So our f of x is going to be, or y is going to be square root of 4 minus x squared. And some of you are already recognizing that this is a semicircle. since y is equal to square root of 4 minus x squared, square both sides, you are going to get y squared equals 4 minus x squared. And you get x squared plus y squared equals 4. This is an equation of a circle where the center is 0, 0, and the radius is 2. Recall that the equation of circle looks like x squared plus y squared equals r squared if the center is 0, 0. And since this is positive, this represents the upper half above the x-axis. If this was a negative, then it represents the semicircle that is below the x-axis. So this is a graph of square root of 4 minus x squared. And in order to find the integral of this, we need to find the area of the semicircle. And how do you find the area of a semicircle? Well, the area of a circle is pi r squared, but we want the semicircle, so we have to divide by 2. And we know that the radius is 2, so it's 2 squared 4, 4 divided by 2 is 2. So area of this semicircle is 2 pi, therefore the integral is 2 pi. Now you got to be careful. Integrals can be positive or negative, or it could be 0. But area is non-negative, which means area can never be negative. It is true that we use integrals to find the area, but remember, area is non-negative, where integral could be negative. And this is what I mean. You have a function over here. If the function is above the x-axis, the integration will be positive. So this is positive right here, and that's positive. I'm talking about the integration. But when the function is below the x-axis, from here to here, the integration will be negative. So when you want to find the area of this area, when you take the integral of cosine x from pi over 2 to 3 pi over 2, what you're going to get is you're going to get a negative value because this function is below the x-axis. Even though the integration is negative, if you want to find the area, which can never be negative, the area of this region will be negative of this integral. And by the way, don't worry about finding the integral of this because you're not ready for it yet. The important concept is you have to understand that area is non-negative, and if you want to find the area underneath the x-axis, it has to be the opposite of integration. So when you integrate f of x from a to b, the integration will be area above the x-axis minus area below the x-axis. So for example, let's say you have this function and you're going from a to b. The area from here to here is 3. And area from here to here is 5. And area from here to here is 4. But what will be the integral of f of x from a to b? For this case, it will be 3 is positive because this is above the x-axis. Now the area here is 5, but the integration is going to be negative 5. And then this is above the x-axis, that's going to be positive 4. So you get 2. Let's evaluate absolute value of x over x from negative 1 to 2. Now our f of x is absolute value of x over x. Go ahead and graph this function, see how it looks like. And when you graph it, you get something like this. Notice it's undefined when x equals 0. In order for functions to be integrable, it has to be continuous within the interval. However, this is discontinuous at x equals 0. So does that mean that we cannot evaluate this? In this case, we are able to evaluate since we could separate them from -1 to 0 and 0 to 2. So what will be the integration of this? Well, the area below will be considered as negative, and area above the x-axis will be considered as positive. So you get -1, because the area of this rectangle or square is +1, but since this is below the x-axis, integration is considered as -1, plus the area of this rectangle will be 2. So -1 plus 2 is 1. Now finally, let's talk about integral of a constant. If f of x equals c, where c is a constant, for example, f of x equals 5, f of x equals -2, okay, where c is any constant, on the interval from a to b, then the integral of f of x from a to b will be just the integral of c from a to b, which will be same thing as c times b minus a. Basically, you're finding the area of a rectangle here. B minus a represents the length of a rectangle, where c represents the width or the height of the rectangle. And depending on whether f of x is above or below, this answer could be negative or positive. So let's evaluate integral of 4 from 3 to 8. When you graph y equals 4 from 3 to 8, you get something like this. So y equals 4 is a horizontal line from 3 to 8. So basically what we need to do is find the area of this rectangle. And what is the length of this rectangle? It's 8 minus 3, which is 5. And what is the height? 4. So 5 times 4 is going to be 20. So earlier we saw that it's going to be c, which is 4 times b minus a, which is 5. So when the function is constant, you don't need to draw any figure. All you got to do is, you know that it's going to be c times quantity b minus a.